Okay, as we get ready to flip over the 3.1 worksheet onto the back, I want to just talk about a couple of things that'll help us with the back side. First of all, you see up here in the top, or not in the top, in the middle rather, it talks about maximum and minimum values. That's the main thing we're going to be talking about on the back side. It says if you have a quadratic function, in other words, if you have a parabola, okay, you can see that there's some maximum and minimum values, at least the y values are. All right. For example, it says if you have a function that looks like this, and we'll see that on the back side of the worksheet. If the a number is positive, then the function is going to have, and remember now, f is y, right? F is the same thing as y, as we talked about in chapter 2. So it's saying that the y values are at a minimum, rather, maximum's down here actually. Y values are at a minimum at x equal to negative b over 2a. That means that the minimum value of y will take place at the vertex, because we know that this is where the vertex is. Likewise, if the a was negative, then the y's would have a maximum value at that same place. If you look down at our graphs right now, you guys, this makes perfect sense because, excuse me, you can see here that when the a value is negative, then since the parabola goes upside down, there is a maximum y value right here. This is the biggest the y value gets, and we saw that with the range, all right? The range, the maximum y value there was equal to 1. And that's what we're going to be looking for here, is that maximum y value. It doesn't, the y values don't go any higher than that, and that's why it's called the maximum. Whereas when the a value is positive, then instead of having a maximum value at the vertex, we now have a minimum value, because the y values don't go any lower than 3. That's why it says down here in the range that the range starts at 3 and then it gets bigger after that, going up to infinity. So with parabolas, in other words, with quadratic functions, all right, the y value will either have a minimum or it'll have a maximum. And there's a lot of good use with that in real life that we'll see on the back side of the worksheet with some word problems. Before I get into that, actually, I'll go ahead and get into that right now. I'll bounce back to some stuff here on the front as needed. But in problem number 4 here on the back, it says a rock is projected directly upward from ground level at an initial velocity of 90 feet per second, okay? So suppose somebody just throws a rock straight up into the air, all right? Now, they probably couldn't do it in 90 feet per second, but maybe they could. But irregardless of how that rock gets projected upward, we need you to imagine that the moment that it starts moving from the ground level on up, it's moving at 90 feet per second. Now, as you know, because of gravity, it will eventually slow down, okay? It'll reach its maximum height, and then it'll start coming back down to the ground again. Okay, it's just a rock. It's not something that's like a rocket that has like a something propelled on it that makes it explode and go faster than it's just the only thing that affects it after you throw it up in the air is gravity. Okay, that's it. All right, not like a rocket. So when that happens, when you just have a free-flying projectile like that, not like a rocket, but just something that is only affected by gravity after it leaves its initial spot, we have this formula right here, s of t equal to negative 16t squared, and then the rest of this stuff. Let me explain all this. I know it looks kind of crazy here looking at it first. Let's write it down on the back side, and I'll give you a little bit of an explanation here on that. I'm going to put the t in a different color here because it's important to realize the difference between t and the other letters there. Sorry, that fell off the screen there. Here we go right here. The negative 16 and this V naught thing, the V0, we call it V naught when the zero's underneath it like that, V naught, and S naught as well. All of those things are constant numbers. Obviously, the negative 16 is obviously a constant, but these two things, V naught and S naught, are also constants. We just need to figure out what they are for that particular problem that you're working on. The only variable here on this side of the equal sign is the t, which is why I wanted to highlight that in red. So what you need to do in the problem that you're doing is you got to look at a couple of things here. First of all, what's the initial velocity? In other words, what's the velocity at time 0? That's why they have the little 0 underneath the V. What is the velocity at time 0? Just before the thing takes off the ground or off of wherever it is. When it starts moving, what is its velocity? Well, you can see here it says the initial velocity, which is obviously a reference to the fact that it's the velocity at the beginning, is going to be what? It's going to be 90 feet per second. So therefore, I'm going to put 90 into that spot right here. Let me do that. So 90 goes in the place of where that V naught thing is right there. Okay. And then what about S naught? Well, because the object takes off at ground level, the S naught will be equal to 0. Now, let's say, for example, somebody had gone up to the top of a 100-foot high building, and then they threw it upward. Well, that would be different. Okay, then in this number would be 100. But because it's at ground level, it's 0 feet above the ground, and that's why we say that S naught is 0. Okay. Now, if S naught is 0, then I would put plus 0 right here. But as you guys know, when you add 0 to something, you don't need to write it. Okay. You can just say, in fact, you know what? I'm going to go ahead and write it right now just to be overly detailed here to make sure you know exactly what I'm doing here. But then I can just rewrite it without the 0 because it makes it more simplified and therefore easier to work with. So let me just write it without the 0 after you can see that the S naught number is 0. So this is the function that they wanted to know here. Okay, it says give the function that describes the height of the rock. So that's when you would use this function that I just showed you on the front side of the worksheet here. That's what that function is when you describe the height of something that is just affected by gravity, nothing else. Okay, air resistance can be neglected as well, even though there's a little bit of it. It's not that big of a deal. Anyway, next question. It says determine the time at which the rock reaches its maximum height. Okay. Notice that this is a quadratic function. Okay, I know it has t instead of x, but it's still that same thing where just like if you have x squared and then x and then no x at all, if you have t squared and then t and then no t at all, it's still a quadratic function, just like the ones that we saw on the front side of the worksheet here, like ax squared plus bx plus c. It's just that it's t instead of an x. Okay, so now because of that, and because of the fact that that a number is negative right there, the a number is negative right here, that means that it's going to be one of those upside, you don't have to graph it here, but it's going to be one of those upside down parabolas if you were to graph it, and therefore there will be a maximum y value. We want to know what that maximum value is because the function, I know this is usually called f, but s is the same thing. We just have a different letter here. It represents the height. So just like the f would normally be the y, this time the s is the y because s is playing the same role that f would normally play. So we want to maximize this function value because it represents the y value right here. Okay, so that's what they mean when they say maximum height. They want to maximize this function value, and we just found out on the front side of the worksheet that function value can be maximized at where? At the vertex. And so all you got to do then, you guys, is take this function right here, figure out what the b is, figure out what the a is, and then plug it in to the negative b over 2a formula, and that'll tell you where this function is maximized. So the b is 90 and the a is negative 16. Let's go ahead and figure out the negative b over 2a fraction, just like we did on the front side of the worksheet. So we got negative 90 over 2 times negative 16. All right, so we figure out what the fraction is equal to first. 90 over 32. Now this time the fraction is not as nice to us. Who knows what 90 divided by 32 is? Well, I don't know it off the top of my head, but that's why we have scientific calculators to help us out. If you put that in your calculator, that's going to be 90 divided by 32. You could put it in decimal form. I'm okay with that. It would be 2.8125. And then when you multiply that by the negative 1 in front of it, just like we did on the front side of the worksheet, it's going to be negative 2.8125. All right. So, you know what? I made a mistake. I'm sorry about that. This is actually a negative 32 down here. I was going to say that shouldn't be a negative answer. And so because of that, let me fix this. So that's going to be, the fraction itself will be negative already because it's 90 divided by negative 32. And then when you have the negative in front of the fraction, that's going to make it a double negative, and that's why it's going to be positive 2.8125. Sorry about that inconvenience there. So, like with any word problem, though, you guys, we need to talk about what is the measurement here. All right. Anytime they give you a word problem that talks about, say, the measurement of something. When you have a problem that talks about, say, feet per second or just feet in seconds individually, okay, that's an example of measurement. Let me just talk about that word measurement for a second because it's going to help us here. The word measurement is anything that makes a number exact. For example, if I said that the top of this piece of paper is 8 inches wide, okay, it's actually 8.5, but that's an exact thing when you say 8.5 inches. But if I say the top of this paper is only 8.5, but I don't say inches, that's not exact, is it? You don't know if it's inches or centimeters or millimeters or what. Okay, but if I say 8.5 inches, then that makes it exact. Measurement is something that makes something exact. All right. You can see here that in this problem, like most word problems, they talk about measurement. And I mention all this stuff about measurement because if you have a math problem, you guys, that has mentioned measurement in any kind of way, and you can see they do here, feet per second, feet, these are things that make numbers exact. When you see measurement mentioned, then your answers should typically have measurement as well, okay? And so we're looking for a measurement. We can't just say 2.8125 anymore like we have in previous problems where numbers as our answers was enough. We got to say how this is measured. Now notice it says determine the time. We all know that time is measured in seconds, minutes, hours, days, those kinds of things. Which one is it? Well, we know that the problem talks about seconds here, doesn't it? Okay, so not that that's the only reason, but that tells us right there that the problem is measuring the time in seconds. Okay, so that's why I'm going to write down second. I know that this is 2.8125 seconds, not minutes or hours or anything like that. Okay, so you got to say that in a problem that talks about measurement, you've got to give your answers in measurement normally as well. All right. Now, it does also ask for the maximum height itself, not just the time in which it occurred, but what is the maximum height? Well, remember, the maximum height is maximizing the y value, or in other words, maximizing the function value, because the function does represent the height. So the height is represented by the function. The function is the same thing as the y value as always. And so if I could figure out the y value that goes with this number, I'm good to go. All right, so just like we were doing with the vertex earlier, you guys, if I plug in the x portion of the vertex into this function value right here, okay, then, and it's going to take some calculator work here, all right, but if I could just figure that out with my calculator's help, then I will then know the maximum height. So let me plug in this decimal into the function at the top of the page there with the -16 and the 90 and all that. You don't need to say +0. Okay, that's not going to do anything. So this ends up being what? You end up squaring this first. Okay, you get that answer. You then multiply that answer by -16, and you get -126.5625. I did 2 steps in one right there. Okay, but it ends up being that. You still got to add, also multiply these two right here, and that's going to end up being 253.125. All right. So if you add those two things together, you end up getting positive 126.5625. That's the maximum height. But remember, you've got to mention the measurement that goes with that answer. Remember, when you're talking about height, you're talking about things like feet or meters or miles or inches. Okay, which one of those is used here in this problem? Well, you can tell that in a couple instances here, they mentioned feet. Feet per second here, feet down here in the next part. And so this must be measured in feet right here. Okay. There we go. And so that's problem. That's part B of the problem. For what time interval will a rock be more than 120 feet above ground level? Okay, well, we know now that the maximum height is 126, and so 120, let's write this down. Again, you don't have to do a graph here. I'm just going to do a visual. Okay, that's 126 right there. 126, I got it from there. I didn't write down the entire decimal. Okay, but I'm sorry, that came off the screen there. Let me back up. So that is basically a picture of what's going on here. Not the picture of the rock, but describing where the rock is. The rock is going to go straight up and then straight back down. But the parabola tells you how the distance changes as the time changes. All right, the time is the time goes like this, okay? The time is along the x-axis because the t is inside of that bracket there, so it's like the x, and that's why it goes along the x-axis. And then the s is like the f there. It's like the y value, so it's along the y-axis. All right, what they're asking here, you guys, is this. If the 126 is up here, what time interval is going to be for is it going to be 120 feet above the ground? Well, it's going to be this time interval right here from this spot to this spot right here. Let me show you. From here to here. Let me highlight a little bit. There we go. Okay, because you can see that from here all the way over to here, from here to here, okay, which is in this time interval. All right, it's going to be above 120, and then it's going to drop back down below 120 over here, isn't it? And then it's going to be below 120 before that, before it gets up to 120 on this side. So if you can figure out what these two numbers are that go with the 120, then you're good. All right, well, once again, as with any ordered pair on a graph, you guys, the y value and the x value make the equation true when they get plugged in together. And in particular, if I plug in the 120 into this function up here, it'll tell me what x values pair up with it. All right, so all I got to do here to figure this out is plug in 120 into this function up here. Let me do that. I'm going to bring that down again. And I'm going to put 120 in there. And that gives me 120 equal to negative 16t squared plus 90t. Okay, if I can solve this equation now, you guys, it will then tell me, again, you can see that I took the s of t up here, brought it down, plugged in the 120. If I solve this equation, it'll tell me what these two t values are equal to. Okay, so once I plug 120 into the s of t up here, I need to solve this equation here. Notice that this is a quadratic equation with one variable, as we learned about back in chapter 1. Because it has the t squared and the t and the constant, we're going to go ahead and move all those terms to one side. It looks like one of those problems where you would normally do that. All right, I'm just going to pull out a quick review of that for you here. Here it is right here. So when you have the variable squared and then the variable and then the constant, it's best to at least try to put that all on one side and then try to factor it if you can. If it doesn't factor, then we can always fall back on the what? We can always fall back on something like the quadratic formula right here. By the way, in either case, you want to take the x squared term and make it positive if it's not already. You can see I did that here by moving that one over. Okay, you can always change the sign of something from negative to positive by moving it over. Well, sure enough, you guys, we have a negative t squared term here. So I'm going to move both of these terms over here by adding and subtracting them over. And I get what? I get 16t squared, put it in this order, 16t squared minus 90t plus 120 is equal to 0. Okay. All right, I'm just going to tell you right now that this thing is not factorable, okay? You could do, other than the fact you can pull out a GCF here, too, which makes it a little bit easier to work with. But it's still not going to be factorable here. So what we can do is, the 2, by the way, if you were to do the factoring, that's not going to contribute anything anyway because there's no variable in it. So you're allowed to, and you'll get the same answer, if you put this thing into the quadratic formula, you're going to get the same answers you would have if you had put this into the quadratic formula. It doesn't matter which one. It's going to give you the same answer because the 2, when you factor out a GCF without a variable in it, that's not going to change the answer at all. And so the quadratic formula will work either way there, as far as getting you the right answer. So what do we get for the quadratic formula? Got to change the sign of the middle coefficient there. Plus or minus, again, this is from section 1.4 if you want to review it. Okay, numbers get kind of big here, but that's why we have calculators. All right. So we got what here? We've got this right here. And as we always do with the quadratic formula, we what? We calculate the inside of the radical first. We get 2025 for the exponent, and then the multiplication part over here is going to be 1920. And so putting all that together, we get 45 plus or minus the square root of 105, all divided by 16. Now here's the problem. 105 is not a square root that we know without our calculator. And when since it's not one of those perfect square numbers like 4 or 9 or 16 or something like that, we have to approximate our answer here. All right, if this was a test question, I will tell you how to round off, okay? Normally, I don't want you to round off unless you're told to, but I did forget to mention that here. In fact, you know what? Let's go ahead and mention it here. Just say round, but I would definitely on the test, round to the nearest tenth, okay? Round to the nearest, actually, let's say round to the nearest hundredth. which is 2 decimal places, you guys. Round to the nearest hundredth is 2 decimal places. And so how does this come out? This one right here is going to be, and if you round off the 105, that's going to be approximately 10.25. All right. And then the other one is just the same thing, but with the minus sign. Okay. Normally, I don't want you to round up before the final answer, but we can do that here. We can do that here. In this case, I'm okay with that. I'm just going to move this out of the way here. Just to, you know what? No, I don't want to move that away, actually. Let me just move this down here. Don't want to get rid of that. It's a good picture. I don't want to get rid of that. So what are these two fractions equal to? They are equal to 3.45 approximately and 2.17. Again, your calculator can help you out with that. Again, what are those two measurements there? Okay, how are they measured? Well, it says what time interval. Okay, in other words, from what time to what time, that's what a time interval is. What time to what time? Well, so since this is measured in according to time, it's got to be in seconds, doesn't it? So the interval, you guys, is the following. It is from 2.17 seconds, okay, up to 3.45 seconds. All right, and we write it like interval notation because it's an interval. Interval notation, right? Okay. There we go. So it's the interval from 2.17 seconds to 3.45 seconds. So that's problem C right there. All right. Last question here on problem number 4. It says, after how many seconds will it return to the ground? Okay. Basically, there's a hard way and easy way to do this. All right. The easy way is to realize that when you throw something up into the air, you guys, this is neglecting air resistance. Okay. The amount of, and again, it comes back to this parabola again. So I'm glad I didn't erase this. All right. The distance that see how the 120 right here, it looks like it's, in fact it is, and we talked about this on the front side of the worksheet. For the same value of y, that distance there, okay, from the axis of symmetry over to those 2 points is going to be the same in both directions. I know I didn't make it look like that. That's not my best parabola. Okay, but this distance right here, okay, in red, is the same as this distance right here in green. This distance in red is the same as this distance in green. And that's the way it is whenever you have 2 points with the same y value. All right, so what that means is that what happens when you return to the ground? The y is going to be equal to 0, isn't it? All right. So the amount of time that it takes, because of this whole thing with the graph, the amount of time that it takes for it to come back to the ground is going to be the same amount of time as it took to get up to its maximum height. All right. If you think about that, and whenever you throw something up in the air, that would be true. All right. Whenever, however much time it takes to get to its maximum height in the air, it's going to take that much time to come back down. How long did it take? It says up here in problem B that it took 2.8125 seconds. And so in order to figure out this final answer right here, you just have to say after another 2.8125 seconds, because it's going to be the same amount of time coming back down. I meant to say another 8 point. Let me put the word another in there. After another 2.81, sorry, it's hard to say these big decimals. After another 2.8125 seconds, the rock will reach the ground again. Okay, so what does all this mean as far as the final answer? Well, if it took 2.8125 seconds to get to its maximum height, and then it took another 2.8125 seconds to get back down. We just need to add up those two numbers and you got it. So what are those two numbers when they're added together? They are 5.625 seconds. 5.625 seconds. That will tell us when it hits the ground. So that's how it works when you throw something up in the air. Okay, so for example, if you threw something up in the air and it took exactly 5 seconds to reach its maximum height, then it would take 10 seconds total for it to go from the ground back down to the ground again. All right, it takes 5 seconds to get to the maximum height and another 5 seconds to come back down for a total of 10 seconds that it's in the air. All right, and that's how it works. Very interesting in my opinion. That is problem number 4. Okay, with all of its different details there. Let's now move on to problem number 5. This one has nothing to do with throwing things in the air, so it has nothing to do with that formula that we did for S of t. Don't use that here in this one. Here we're talking about, well, let me just go ahead and read it here. It says, a farmer wishes to enclose a rectangular region bordering a river. And I have a picture of it down here at the bottom of the page. You see the river right here on the top part, and then we have 4 pieces of fencing down here. These 3 parts are all the same going up and down. That's why they all say X on them. It's because they're all the same. Okay. This side down here, though, we don't know what that is yet. We're going to talk about that, and that's going to be really important. All right, but this is basically what the farmer's doing. He is building a pen probably for his cows and pigs and his animals and stuff, but it borders along the river there, okay, because your typical animal's not just going to jump in the river, so that keeps them protected from getting out. Because it's along the river there, we only have fencing along the short end like this with the 3 X's, and then also along this end, but not against the river. You don't need a fence against the river. That's basically what's going on. It says X represents, oh, we already talked about that actually. Now she has 600 feet of fencing available. Okay, this farmer does. And so 600 total feet of fencing. So in other words, these 4 pieces, you guys, the X, the X, the X, and then this bigger side down here, all of that has to add up to 600 total feet. Okay, that's all that she has available to her. And so maybe she doesn't want to buy anymore for whatever reason. All right. So based on that, what is the length of that remaining piece of fencing, the part that goes this way? Okay. The way to figure that out is like this. We already know that the other 3 pieces are X. And so if I add those together, all right, that's equal to 3X, isn't it? Remember, you can add these together because they're like terms. And so we combine like terms, we get 3X. So that means what? That means that 3X plus that missing side right there, I'll put a question mark right there, is equal to 600. Well, if I put a variable there, you guys, just to fill that in with something mathematical instead of a question mark, I'll just call it the letter M. You can call it any letter you want. But I want to figure out what that thing is, whether there's a question mark there or whether there's a variable there. It doesn't matter. How do I figure out that thing? Well, I figure it out by getting it by itself on that side of the equal sign. Just like any equation where you're trying to figure out a variable, you get it by itself. And you guys know that you can do that by subtracting the 3X over. Okay? Because anytime you have a variable being added to something and that's it on that side of the equal sign, you can subtract that other thing over to get that variable by itself. So M is going to be what? M is going to be 600 minus 3X. That is what that bottom side is equal to. Let's go ahead and write that down here. Okay? So 600 minus 3X is now that bottom part right there. Let me zoom in there just so you can see what I wrote down. 600 minus 3X is going all the way across the bottom here. Okay? Now, let's go back up and take a look at problem B. It says determine a function They call it A because it's going to represent the area. You could call it F if you want to, theoretically. It's just a function, but it does represent the area, so they give the name A there just to make it easier. But it represents the total area of the enclosed region. Total area. And then it says give restrictions on X. We'll get to that. So the area, you guys, by definition, because this is a rectangular shape down here, the area is what? It is found by taking the length times the width. Anytime you have an area of a rectangle, it is found by taking the length times the width. You might be wondering, well, what's the length and what's the width? I don't remember how to do that. Well, the length and the width of a rectangle is any two sides of a rectangle, you guys, that meet at a corner of the rectangle. Now, remember, I'm talking about the entire rectangle. I'm not talking about just one of the smaller rectangles like this. I'm talking about the entire thing here. It says in the problem the total area of the enclosed region, not just part of it. So, looking at this right here, this is a corner of the entire region. You take two sides that meet at that corner and multiply those together, and I promise you that's the area. All right, I don't care what corner you pick. Just don't pick a corner in the middle here, because that corner is only for this side and this smaller side right here on the right. That's not the entire region. That is just for the rectangle, this smaller rectangle. Okay, we want a corner of the entire rectangle, and we want to multiply the entire side over here of that rectangle times this entire side of the rectangle down here. Okay, not just a smaller side. Okay, you got to do, once you find that corner, you got to do the entire side over here and the entire side over here. All right, so that's the difference. Not the smaller amount, but all the way across, because we're looking at the whole thing, the entire rectangle, the big one. All right, now, so that would be what? That would be x times 600 minus 3x. Those two sides that meet at a corner that I just showed you, that's what they are. Again, put this in brackets because it's got two terms separated by a minus sign. That tells us this is two terms. And it's being multiplied by something other than positive 1. So you got to bracket it. Okay. So that is your function. We can go ahead and simplify that to make it look like, you know, one of those functions that doesn't have brackets in it. We have 600x minus 3x squared. I'm going to go ahead and reverse that around. It's not totally mandatory, but it's going to make this easier. Put the x squared term first. That's what we usually do. And you can see there that that is similar to, once again, this type of function. It's just that it's missing the c, but that's okay. That just means the c is 0. Okay, as long as you have constants, including the invisible 0 there, as long as you have constants a, b, and c with the variable squared and then the variable here, that is a quadratic function. Even if you call it ax, that's still okay. It's just a different name, but it's still a quadratic function, and so we can assume that it's going to have the maximum and minimum values and all that kind of stuff. That's going to help us here. So, before I get into all that, we know there's a quadratic function. Now we know that it's a parabola if I graphed it. Not that we're going to, but it is one if we did. But most importantly, it's going to, because this is negative, that means the graph is going to go upside down. And that means it will have a maximum value at the vertex, won't it? Okay, it will have a maximum value. All right, but before I talk about that maximum value, a few other things first. It says, what's the restrictions on x? And that's important here because we don't want to end up dealing with x values that don't make any sense. Here's what I mean by this. We have a total fencing of 600, right? Looking down here at this picture, we have a total fencing of 600. Isn't it true that x could never be bigger than 200? In fact, it couldn't even be 200. Okay, because if you had 200 here, you'd then have to have 200 here and 200 here. 200 plus 200 plus 200 is 600. That would leave you with nothing left for this bottom part, wouldn't it? Okay, so x has to be, the restrictions in other words, the restrictions have to be so that x is less than 200. Okay. If it's less than 200, that will still leave you with enough fencing for the bottom part down here. Okay. Now, what's the other restriction? There's another restriction. The other restriction is the fact that x obviously has to be greater than 0. Okay. You can't say that I've got -2 feet of fencing. All right. There's no such thing as -2 feet or negative of any kind of feet. Okay. When we talk about feet or any kind of distance, it's always a positive thing. It's not negative. Okay, so x has to be between 0 and 200. So just in case we run into an issue there where we get a number outside of this range of values between 0 and 200, then we'll know that we need to get rid of that possibility. Not saying that's going to happen, but sometimes it could in some future problems. Next part here says, what dimensions for the total enclosed region would give an area of 22,500? Now remember, AX is called A for a reason. It's because it is the area. And so if they say, hey, the area is 22,500, then we plug 22,500 into the AX right there, just like plugging a Y value in to a equation and figuring out what the x is that goes with it. We did that many times when we were graphing lines back in Chapter 2, where you plugged a y value in, and then you had to figure out the x value that pairs up with it. This is no different, okay? Since the a is the y value here, okay, and since the area is 22,500, we plug that into the a, and then we figure out what x value is going to pair up with that. This looks very similar to the previous problem where you've got a quadratic equation because of the x squared. All right. I'm going to move all the terms to one side, but I'm going to move them in such a way that the x squared is going to be positive, because that's typically the best way and sometimes the only way to do it when you're either doing the factoring method, the zero factor property from Chapter 1, or the quadratic formula. Now this time, even though these numbers are huge, you guys, this actually is factorable. So I'm going to factor out the 3 to make the numbers a little bit more manageable. You should always factor out the GCF anyway. And according to our knowledge of factoring, we know that we need a product of 7,500. So the 7,500, that needs to be the number that the two numbers need to multiply together to be, and they need to add up to -200. Okay, as we did back in our review. Okay, you list out the factors of 7,500. I know that's a really big number, but because it's a nice even number with the 0, 0 on the end, it makes it a little easier. But ultimately, let me just cut to the chase here. That's going to end up being -150 and -50. You just need to use your calculator to help you out with that. You do, like, for example, you do 1 and 7,500. Oh, that doesn't work. And then you do 2 and 3,750. Oh, that doesn't work. And eventually you'll get to the point to where 50 and 150 will work to equal 7,500. But you need to make them both negative in order for it to add up to -200 while still multiplying together to be 7,500. So just a little review of that, of the factoring there. Okay. So it becomes this right here. X minus 150 and x minus 50. And then with the zero factor property, we set those factors equal to 0. Okay. And we get two answers here because that first thing right there, the 3 equal to 0, that's not going to give us anything. All right, when you have an equation with no variable in it, okay, and it's false, 3 is not equal to 0, as you know, then of course that's going to be no solution, as we learned before with equations. We learned that in our prerequisite review as well. So no solution on that. This one is x equal to 150 if I move the 150 over. This one is x equal to 50 if I move that over as well. So we get what here? We get two possible answers. We get x equal to 150 and x equal to 50. But here's the thing, though. They want to know the dimensions. The dimensions means what when you're talking about a rectangular region? It is the length and the width. The dimensions is the length and the width. Remember, you guys, the x is just one of those things down here. The x is just one of those things. So you might be wondering which one is it, the length or the width. Well, the length and the width of any rectangle, you guys, is any two sides that meet at a corner again, like I was talking about earlier with that whole corner discussion. All right. But we're talking about the big rectangle here again, not the smaller one. So if this is, for example, the length, then the 600 minus 3x would be the width. And vice versa. If you called this the length down here, then the x would be the width. So it doesn't matter which one is which. The point is that the x is the 150 and the 50. Yes, there's going to be two possible answers here. Okay. So whatever if this, for example, is 50, then you plug in the 50 into that to figure out what this side is. Let's go ahead and do that right now. Okay, so I'm going to do that for 50, and then I'll also do it for 150. So for 50, the other side, the bottom side there with the 600 in it, that's going to be equal to what? That's going to be equal to 450. Okay, let me give myself some more room here. And so that's going to be 600 minus 3 times 150 now, and that's 450 on the multiplication, so that's going to be 150. All right, what did we just find out? Let's go through this carefully. It says here that when the x is 50, the bottom side is going to be 450. So 50 feet by 450 feet is one of the possibilities here. 50 feet by 450 feet, okay? Or what? Or the other possibility is 150 paired up with what? 150 paired up with 150. So the other possibility is 150 feet by 150 feet. Okay? Sorry, I kind of ran into the river there, so to speak, okay? 150 feet by 150 feet. And so there's two different possibilities right there, all right, for when the area. So if you really want the area to be exactly equal to 22,500, then, and you're this farmer right here, then you've got a choice. You could either do the 50 by 450 setup, which would be a very narrow, skinny pen, or it could be more like a normal rectangle, 150 by 150. Okay, in fact, that would look like a square, as a matter of fact, which is also a rectangle, as it turns out. So that's either one of those things would give you that area. All right. So solve that for the x, but remember the x is just one side, and you got to figure out this other part here to figure out the length and width together. Finally here, what is the maximum area? Well, just like in the last problem, maximum has to do with the maximum y value. And as we talked about, the maximum y value always takes place when you're talking about a quadratic function like this is right here. Let me put it back up here. Like this is right here. And therefore it's represented by a parabola. That maximum will always take place at the vertex. But the vertex, you guys, is where? The vertex, let me write this down, at the vertex, okay, and because it's at the vertex, we're going to use what? We're going to use negative b over 2a in order to find that out, all right? And so let's figure out negative b over 2a again. Okay. What is the b and the a in this problem? The b and the a in this problem are, the a is negative 3. I'm just taking it right. Sorry, that came off the screen there. There we go. The A, I don't mean the big A over here, I mean the little a, when you have ax squared plus bx plus c, that's what I mean. The little a is -3, and the big A, or the B is the coefficient of x, as always, and that would be 600. So plugging that in over here, move it over, plugging that in over here, I get -600 over 2 times -3. What is that fraction equal to before we multiply it by the -1 that's in front of it? Okay, it is equal to the fraction is 600 over -6. That's equal to -100. Then when you have the negative in front of the fraction, that's going to create a double negative, which makes it +100. Okay, so that is the x coordinate of the vertex. But as you guys know, the maximum occurs at the y value. We just use the x part of the vertex to find that y value by plugging it in. Okay, so the maximum value occurs at the 100, because that's the x value, but the actual maximum value itself is the y value that you get when you plug that x value in. So we're going to plug the 100 in to the a value, the a function, pardon me, up here, okay, because that's what we're trying to maximize, is the area. And we get -3 times 100 squared plus 600 times 100, and that is going to be equal to exponents first. I get -3 times 10,000 plus 600 times 100. Let me get this out. You know, I need to get that out of the way there. Let me just move it up a little bit. I'll put that up here. A is equal to -3 and B is equal to 600. Okay. Then I multiply and I get -30,000 plus 60,000. And what does that equal to? -30,000 plus 60,000. That is equal to, calculators, 30,000, but 30,000 what? Well, area, you guys, as you probably heard before when people talk about putting carpeting or tile inside of a room or something, area is always measured in square something, whether it be square feet, square miles, square inches, square meters, all right? Because this is a feet problem, and in fact, they give you a clue over here anyway. They say area of 22,500 square feet. So you can see right there that that's how they measure area, but it's always going to have that square thing in it. So this is 30,000 square feet. That is the maximum area that this farmer could achieve with that 600 feet of fencing that she has available to her. Okay, and so that's a good thing to know. All right, she wants to be able to maximize the resources that she has, right? Okay, and the resources she has is 600 feet of fencing, and so that's what she can get out of it. 30,000 square feet for her animals, all right, or whatever else she's going to put inside the pen. And so that concludes our discussion here in 3.1. And so, as always, let me know if you have any questions. Take care.